Performing finite element analysis, or FEA, on a bone model can be useful for research applications such as simulating an implant's performance, contact force analysis, and shear stress examination. Now, in order to perform accurate and reliable simulations, it is important to provide a proper mesh structure with surface and volume elements. In this video, we will show a typical workflow in the Mimics Innovation Suite, where we will start from segmented medical images and go to a pre-processed model ready for FEA. You will learn how to mesh a 3D model in 3matic and then how to assign material properties to it in Mimics. We start with the femur FEA file in Mimics Core, and then here we copy the wrapped femur object and paste it into 3matic. In 3matic, let's rename the object to femur and change its color to that of a bone. We can do this in the Properties tab on the bottom of the interface. And here you'll also find extra information about the object, such as its volume and the number of triangles that it's made up of. We can visualize the surface mesh of the bone by changing the view to show the edges of the triangles. And this can also be done by using the shortcut Shift F3. Now we can see that the mesh of the bone is pretty rough and irregular in some places. Now, to do a proper finite element analysis, we want the mesh to be smoother and more uniform. A first step to achieve this is to smooth the part with the Smooth tool under Fix menu. For this specific case, we select a smooth factor of 0.7. The next step is to make the triangles of the mesh more uniform. In the Remesh menu, we can find the Uniform Remesh tool. This tool allows us to remesh a part with a certain target edge length. For this specific application, we set the edge length to 1.5 millimeters. And before clicking on Apply, we can see an estimation of the number of triangles generated, as well as the memory usage to perform the operation. After clicking Apply, we can clearly see that the mesh is now much more uniform compared to before. The next part of the workflow consists of creating a volume mesh. But before we do this, it is important to check our part for intersecting triangles. An easy way to do this is with the Fix wizard. Select all items from the diagnostics list except overlapping triangles, as they are not so relevant for creating a volume mesh. Now click on Update. The Fix wizard will show the number of problems detected. To solve those problems, simply click on Follow Advice until all the values turn green. It is very important to always use the Fix wizard before creating a volume mesh. Now we can actually create a volume mesh with the tool under the Remesh menu. In order to achieve a uniform mesh inside the model, we'll set the maximum edge length slightly larger than the maximum edge length of the surface mesh. So in this example, we'll use 2.5 millimeters with TET4 elements. One thing to note is that the edge length will have an influence on the number of volume elements created, and that in turn influences the calculation time in the solver program. In the logger, we can see that the volume mesh has been created successfully. Now let's visualize it. We can do this by going to the section list in the object tree and right-clicking on the standard Y section to show it. Then we can turn on clipping and change the position of the plane. And this is a good way of visualizing the volume mesh that we have just created. We can gather more information about the mesh when we go to the object tree of the femur and click on Analyze Mesh under the metadata. At this point, it is still possible to convert our mesh from TET4 elements to TET10 elements. TET10 elements are better than TET4 elements for stress analysis in structures and solid mechanics. In the Remesh menu, we can find the Convert Volume Mesh tool, and there we have to select the femur and the correct conversion before clicking Apply. Now let's save this project before we continue in Mimics Core. In the last part of the workflow, we will assign material properties to the volume mesh. To transfer the volume mesh back to Mimics Core, select it in the object tree and press Ctrl+C. Then open Mimix Core and press Ctrl+V. The mesh will appear in the object list as a cube with dots on its corner. In the FEA menu, you'll find the Assign Material tool. Here we can assign a density, a Young's modulus, and a Poisson ratio. Select the femur copy and press OK. There are several methods for assigning material properties, but for this exercise we will go for the gray value-based method. This means that we will assign the properties of the volume elements based on the corresponding Hounsfield units on the CT scan. And this assignment will be divided in two types. For all voxels with Hounsfield units of 100 and lower, we will just assign a single density value of 50 kilograms per cubic meter. And for the Hounsfield units of 101 and higher, instead of assigning a constant value, we will assign a lower and upper value and then divide the interval into 10 parts with ascending densities. Apart from the density, we can also assign the Young's modulus and Poisson ratio, but these, however, will be the same for the entire range of Hounsfield units. Let's start by clicking on the plus icon next to Material Type 1 to create a new tab. For Material Type 1, we set the minimum gray value range to -90 and the maximum to 100. Next, we fill out the material parameters below. The density is 50, and for the Young's modulus, we fill in 0.004 and 2.01. For the Poisson coefficient, we fill in 0.3. In this step, ensure that the values are entered in the correct text box. Now we can do the same thing for Material Type 2, only there the density will be a range and not a constant value. Click on Material Type 2 and set the minimum value to 101 and leave the max gray value at its default value. Then, before filling out the density, make sure that the first option is selected. For point 1, 100 Hounsfield units corresponds to a density of 50 kg per cubic meters. And for point 2, we fill in the maximum Hounsfield units, and that will correspond to a density of 1900. In the end, click Apply to assign the material properties to the femur, and then click Close to end the material assignment. We can again visualize the volume elements now by launching the clipping tool. Select the coronal view and toggle the texturing to None. And we can see that the model gets clipped through the coronal view and that the clipping plane changes based on the image that we see in the coronal view. As a final step, we can export our mesh with its properties to our desired solver program. Under the File menu, click on Export, then on Meshes, and there, select the relevant program. Select the femur copy mesh, and after having selected an output directory, click on Apply. From the File menu, we can now use the Save As tool to save the project under Femur FEA Final. And with this, we've arrived at the end of our exercise.